Okay, now that we've looked at the basics of capacitors and inductors, let's consider how we're going to do circuit analysis for the rest of the semester using these circuit elements. So one of the first things we need to consider is, this is a class in linear circuit analysis. So the question is are capacitors and inductors linear elements? I mean, do they actually fit into what we're trying to do in this course? Well, let's consider this. I is equal to C dV dt, for example, for a capacitor. Or to put it more accurately, I of t is equal to C dV t dt. So let's define this voltage. Let's let V of t equal to A times V1 of t plus A2 times V2 of t, where A1 and A2 are just arbitrary constants. In other words, I'm saying that V of t is the superposition of two different voltages. That's exactly how I'm expressing this. Okay, so let's take that then, and let's plug this into that equation. What we get then is that I of t is equal to C times the derivative of A1 V1t plus A2 V2 of t dt. And if we take this derivative, we can break this into two parts. This will be equal to A1 and A2 are constants. They could be factored out of the derivative term. And so I can write this as A1 times C dV1 dt plus A2 times C dVt2 dt. So the current can be expressed in this form, which, if you'll remember, this is the definition of linearity. So I could do a very similar type of expression using V is equal to L di dt for the inductor, and also show that once again that also meets the definition of linearity. So, not surprisingly, and very fortunately, both capacitors and inductors are linear elements. So just like the sources we've looked at, just like resistors, they're linear, which means, therefore, everything we've learned so far works. KCL, KVL, superposition. Thevenin's theorem. Norton's theorem. All of these apply to circuits that contain capacitors and inductors. So everything we've learned so far still works. Now, granted, the math is messier because we're using integrals and derivatives, but everything does still apply. All those principles still apply. So let's look at a few basics that we know right now or can easily prove to ourselves about how to analyze circuits that contain these elements. First of all, and we've already seen this, we've discussed this, capacitors and inductors behave in a particular way in a DC circuit. So we've talked about this before. DC circuits versus AC circuits. And it's worth repeating. In a DC circuit, all voltages and currents are constant. In an AC circuit, the voltages and currents will change with time. So these go all the way back, as I said before, to when we were first running electricity all over the country. Direct current versus alternating current. Now they have a broader definition. Things that do not change with time versus things that do change with time. So, in a DC circuit, or rather in DC conditions, DC operating conditions, capacitors act like open circuits. And inductors act like short circuits. So we have a capacitor, we have an inductor, and in DC operating conditions, we know that I is equal to C dV dt is equal to 0, V is equal to L di dt is equal to 0, because the voltages and currents aren't changing. And so for a capacitor, we will have 0 current flowing through it. For an inductor, we will have 0 volts across it. Now you can have a non-zero voltage across the inductor, or pardon me, across the capacitor, and we can have a non-zero current flowing through the inductor. But the current through the capacitor and the voltage across the inductor must be equal to 0. And as we said, you can really kind of think of it this way. The capacitor is really behaving just like an open circuit as far as circuit analysis goes. No current flows through it. The inductor acts like a wire, like a short circuit. No voltage across it. So given this, let's work a simple example. What if you were given a problem like this? Let's find IL and VC with the following circuit. And in this case, the 10-volt source, notice I'm saying this is 10 volts DC, VDC. And you'll quite often see me use this kind of nomenclature as we move further into this course and we start seeing AC versus DC. So in this case, I want to go and find this. Well, actually, it's not that difficult at all. If I ground that node, this is 10 volts. This is VC according to the way I defined this. That current is equal to 0. I also know the voltage across this, and actually I forgot to draw the I sub L, so I'll add that. So I know that the voltage across this inductor must be equal to 0 volts. And in fact, let me do this in a little bit different color to kind of keep this from getting too confusing here. Let's do it this way. So this current's equal to 0. This voltage is equal to 0 volts. There we go. A little bit clearer that way. So given this, if I've got VC on this side, that means I've got VC on the other side. And now I can go through and say that in this case, this current and this current are flowing through those two resistors, and therefore 10 minus VC over 1,000 must be equal to VC, and pardon me, give that a value, that's 1K, and that's equal to 1,000. And therefore, I can calculate VC. VC will just be equal to 5 volts, and IL will be equal to 10 minus 5 divided by 1K, and that will be equal to 5 milliamps. And there are my voltage across my capacitor and current through the inductor. I could have done this a little bit differently. Could have just done this. Could have just erased that capacitor, made it into an open circuit. Could have just taken that inductor and just turned it into a wire. And then it's very easy to see what you need to do. I just have a voltage divider here. So VC is just equal to 5 volts, and therefore 5 divided by 1K is 5 milliamps, and that's the current flowing all the way around the loop. And I get the same answer. So as you can see here, in a DC circuit, capacitors and inductors are easy to deal with. They're just going to be effectively open circuits or short circuits. Now, what if we are dealing with AC circuits? Well, let's draw a possible example. Let's draw a simple AC circuit here. Let's instead look at this. What if you've got a problem like this? Okay. I want to find the voltage V1 across this capacitor. And notice in this case, the voltage and the current are both sinusoidal functions, sine and cosine of 10t respectively. And I want to find V1 of t. And I'm going to assume there's no initial condition in either of the capacitors. Now here things get tricky, because if you look at this, you're going to have to apply the IV relationships for capacitors. V is equal to, pardon me, I is equal to C to V dt, and V is equal to 1 over C integral of I dt. Now, this may actually look pretty intimidating, but this is not that difficult a problem to solve if we use a circuit analysis technique we're very familiar with. Let's use superposition. So it turns out I can draw the circuit like so. I've got two independent sources. So first I'm going to zero out the current source, and I have this. Then I'm going to zero out the voltage source, and that will give me this. So in this case, I've still got 1 microfarad capacitors. This is 5 times sine of 10t volts. And this is 10 times cosine 10 of t microamps. And in this case, I want to find V1 prime, and here I want to find V1 double prime. So let's solve for each of these. Now, breaking it apart this way, now this is something we can tackle because we can combine these capacitors together. This is 2 capacitors in series. This is 2 capacitors in parallel. Notice they're both connected to the same 2 nodes. So in this case, I'm going to define, for this problem at top, I'm going to define a current I prime. And so I'm going to write the equations for that. My equivalent capacitance, CEQ, is going to be equal to 1 microfarad plus 1 microfarad is equal to 0.5 microfarad in series. And so in this case, what I have is that I prime is equal to CEQ dVdt, so that's the voltage of this source, and therefore this will be equal to 0.5 microfarads times 50 times cosine 10 of t volts. So when I take the derivative, sine goes to cosine, 10 times 5 is 50, and that's my current in amps. And this will be equal to 25 times cosine 10 of t microamps when I multiply through. And now that I know that, I want to find the voltage across this capacitor. So therefore, V1 prime will be equal to 1 over 1 microfarad times the integral of that current. So the integral of 25 cosine 10 of t times 10 to the minus 6. And if I take that integral, what I'm going to get is this will be equal to 2.5 times sine 10 of t volts. So I found the current, then I integrated the current to find the voltage just for that one capacitor. Over here, in this case, V1 double prime will be equal to, in this case, the equivalent capacitance, CEQ, is equal to 2 microfarads because they're in parallel, they're going to add together. And so in this case, this just disappears, and this becomes 2 microfarads with the V1 prime across that, and V1 double prime, or pardon me, the V1 double prime across it, and V1 double prime is going to be equal to 1 over CEQ times the integral of 10 times cosine 10 of t times 10 to the minus 6, and this is equal to 2 microfarads. And if I go through and evaluate this integral, what I'm going to get is this is equal to 0.5 times sine 10 of t volts for V1 double prime. And therefore, V1 is equal to V1 prime plus V1 double prime will be equal to 3 times sine 10t volts. And there's my solution. So that can be solved. If we went through and applied a little analysis trick, that's doable. I mean, granted, you're still doing calculus with it, but it's just simple simple integration and differentiation. It's not impossible to do. But there are other problems that are much trickier. Let's consider this problem. What if we had this? Okay, let's say we had, in this case, Vs is equal to 10 times cosine 100 t volts. And given that, I want to find Vc. How do I find the voltage across the capacitor? Well, let's go through and see what kind of equations we need in order to solve this. So in this case, writing KVL around the equation says that 10 times cosine 100t must be equal to VL plus VC. And I've got a current I that flows around this single loop circuit that I'm going to define. And this current I must be equal to C to VC dt. All right? So I know that must be true because of the capacitor, same current flowing through it. VL, the voltage across the inductor, must be equal to L times di dt by inspection. So I can take this I, take the derivative, plug it into here. So this is equal to L times C times the second derivative of Vc with respect to time. So therefore, I can write this equation, 10 times cosine 100t must be equal to 160 times 10 to the minus 6 times the second derivative of Vc with respect to time plus Vc. So now I've got an equation in terms of Vc with a second derivative term in it. So this is a second order differential equation. So this circuit with 3 elements requires a second order differential equation. Fortunately, this is not particularly difficult to work. Let's do that. Let's assume that in this case we're going to guess at a form of the solution and see if it works. Let's assume that Vc has the form, in this case, Vc equal to A times cosine 100t volts. So I'm going to assume that it has that form. I'm going to plug it in. So I'm assuming it is some fraction of that original voltage. So let's go ahead, or it's basically, it's some multiple, some constant multiple of that original voltage. So let's go ahead and do that. And so what we're going to get is, therefore, that the Vc dt is therefore equal to minus 100 times A times sine 100t. And the second derivative of Vc with respect to time is equal to minus 10,000 A times cosine 100t. So I can now take this and plug this back into this equation. And so what we're going to get is that 10 times cosine 100t is equal to 160 times 10 to the minus 6 times minus 10,000a times cosine 100t plus a times cosine 100t. So I've just substituted my second derivative term back into this. And what do you know? These cosine 100t terms cancel out. And I can solve for a. And a will be equal to minus 16.667. And therefore, VC is equal to minus 16.667 times cosine 100t volts. And it works. But it's not easy. And keep in mind, that's a circuit with 3 elements. Imagine what would happen if I had a circuit with multiple elements, multiple meshes, multiple nodes. Well, the problem is very quickly doing this with calculus becomes impossible. It simply really isn't humanly doable. So what we find ourselves is in a situation where using standard calculus to solve circuits in the time domain that include capacitors and inductors just doesn't work. We need better math, okay? And later on, I'll show you that better math called phasor analysis. So we're not really going to try to solve circuits in any significant way from this point on by trying to do second-order differential equations. It just isn't going to work. Any kind of calculus you see are usually going to be simple first-order equations. And when we get to the point where we start looking at more complex circuits, we're going to be dealing with sinusoids, and then you'll learn all about phasor analysis, which makes the math much, much easier to deal with. In particular, it makes things very easy to work with when you're using a piece of software like Mathematica, which can easily handle complex variables. Okay? All right, so next time, let's take one final look at capacitors and inductors and how we can apply them to some simple op-amp circuits. And in doing so, I'm going to show you guys a very interesting application of the way that op-amp circuits used to be used in terms of computing, which we don't use anymore today. And that's called analog computers. So we'll look at that next time.